Okay, so we're now on to chapter 4, which is kinematics. We've actually looked at kinematics before because it's been featured in normal maths mechanics. So this is going to feel very, very familiar. There's just a couple of little things we add in. So I think you'll find this quite a straightforward one that we've got here. So when we look at this, the remaining chapters for further mechanics 2 are kinematics and dynamics. Now I wanted to kind of talk about both of them together to begin with, just because they sound similar, and actually the majority of things that are going to happen for both of these things are integration. So kinematics concerns itself with the study of motion. If you think of that word kinetic is obviously to do with movement. So kinematics is just the study of motion. That's things like acceleration, velocity, displacement, and time, all of those things linked together. Dynamics, which is chapter 5, on the other hand, is the study of forces and how they produce movement. So really dynamics is going to build on everything that we learn about in kinematics. Kinematics is the AS kind of version, and then dynamics is the stuff that you'll see featured more in A2. So like I've said, both of these chapters are going to be very integration heavy. So if you haven't learned the following things, you're going to find this pretty tricky, and I'd recommend doing this right towards the end. If you finish with kinematics and dynamics, you'll be in a pretty strong position to be able to answer most of these questions. So a little bit of the prerequisite knowledge that you need. You do need to know how to do integration from pure year 1 and pure year 2, and you must make sure that you know how to do differential equations. You will eventually need to know some of the ideas from differential equations in core pure year 2. That's going to be used a little bit more in dynamics, but very light touch. It's mostly the differential equation stuff in the first exercise that's featured in normal maths as well. And obviously, you're going to need to do variable acceleration from year 1, because variable acceleration from year 1 is where we touch on most of the stuff to do with kinematics that we've learnt so far. Now, the reason I've put just year 1 is because further mechanics 2 kinematics only concerns itself with moving on a straight line, so no vectors, nothing for 2D kinds of stuff as well. So there's only 3 exercises for this. We look at 3 different kinds of kinematics. We do it where the thing that we're studying, whether that's acceleration or velocity, is a function of time. Then we do it where it's a function of displacement, which is only in A2, and then functions of velocity. And I've said this is partly in A2, because if you look in the textbook, you'll see that some of the questions have got some like A2 integration in, but this is stuff that could come up in AS. Obviously, the integration would be slightly easier for those if it was in an AS paper. And of course, as usual, I'll do some exam questions that come at the end. So I've just got a little box here because it's going to actually teach us everything we need for exercise 4A. Just a quick recap of mechanics from year 1, all of those things that we need to know how to do. Now, I've written them in this order where I've got the displacement, which is usually X or S. I'm pretty much going to use X the whole way through this thing though. We have the velocity and the acceleration. When they're written in that order of SUVAT, S, U, V, A, T, if you want to go from S to V to A, hopefully you remember that to go down that list, you just differentiate with respect to time. And if you wanted to go up that list, say from the acceleration to the velocity, then we know that you just integrate whatever that function is with respect to time. So down differentiate, up integrate. And this is going to be an incredibly familiar sort of first video that we've got here, because it's basically a recap of everything you should have done in the variable acceleration of mechanics in year 1. So here are where we have things expressed to us as a function of time. Well, we've just talked about this part here, that if you wanted to move from S to V or V to A, you differentiate. And if you wanted to go up that list, you integrate instead. A few different things about notation that you might see when we're doing this kind of thing. First of all, displacement, we're going to use the letter X. You might see the letter S, but I would say that X is definitely going to be the more common one out of those 2 that we've got. Now, velocity, you should know that velocity is the derivative of the displacement, dx dt. Obviously, we can use the letter V, and maybe you've seen this notation before, this dot notation. The X with the dot above it just means it's been differentiated with respect to time. Now, acceleration, we have A, we have dv dt, because we know that it's the velocity differentiated, or we could say it's the displacement that has been differentiated twice, so I've got that second derivative of x there. And last of all, because it's been differentiated with respect to time twice, we put 2 dots above that x to represent this. Now, I'm not actually going to answer this question. I'm just going to kind of explain how we would do this. This is kind of the style of thing that you would have had in mechanics from year 1 with variable acceleration. They would have given you this velocity that we've got here. I'm not sure why I put this in terms of x. This should obviously be in terms of t, so I will change that on the PDF. And I've drawn a sketch of this velocity time graph that we've got here, and I've said to find the distance travelled in the first 6 seconds. Now, I hope you might be thinking what you need to be doing very carefully to answer that question. And the bit you need to do very carefully is to make sure that you do the part at the bottom separately, because anything that dips below the axis is going to have a negative area. So we would need to consider this for 3 different time intervals. We would have to integrate v between 0 and 2. And then instead of adding on this part, because it's going to be negative, if I subtract it, it will effectively add it on. So I'm going to subtract between 2 and 5. And then my last thing that I would do is I would add back on the 5 and 6 that we've got there. And so really this is just my warning of be careful of negative areas. Exactly the same warning that we would have had when we were looking at this in year 1. And one of the ways we can often see that there's going to be a change in a change to a negative area is often if the question says that there's like a change of direction, or it might say that the particle comes to rest, because we can see here the particle will be coming to rest. Will it be changing direction for these kinds of things? When it comes to instantaneous rest, it kind of switches around. If it ever talks about maximum displacement, we know that the maximum displacement occurs when the velocity is equal to 0, or when dx dt is equal to 0. You can almost think about it as like the turning point on the graph. And similarly, the maximum velocity is reached when the derivative of v with respect to time, when the acceleration is equal to 0 that we've got there. So really just a complete recap of everything that we've done in year 1. I'm going to do 2 examples, and then you can have a go at the third one. So I've said here that exercise 4A is the same kinematics content from normal maths, the same variable acceleration stuff, but often the integration might be a little bit harder. So if you are doing this in a school, you're going to want to make sure that your teacher has shown you how to do all of the different bits of integration. And at some point, I'm hoping to do a kind of like crash course in integration, just to kind of give you the, how do you integrate as quickly as possible without having to learn the whole chapter. Anyway, it says a particle is moving in a straight line with velocity at time t seconds, given by v equals 4 sine 2 pi t meters per second. The particle is at O at time t equals 0. Find the magnitude of the acceleration when t equals 2/3. Well, if I want to find out for part A what the acceleration is, we know that the acceleration is the derivative of the velocity. So all I'm going to do is differentiate this thing. Now I'm going to assume you know how to do the chain rule here. So there's going to be the 4, and we're also going to have to multiply by the derivative of this inside part, which is 2 pi. So that is 4 times 2 pi, and sine differentiates to cos. So it's going to go to cos of 2 pi t. So it is 8 pi cos 2 pi t. And we just want to find out what the acceleration is when t is equal to 2/3. So when t is equal to 2/3, the acceleration would be 8 pi times by the cos of 2 pi multiplied by 2/3. So just on my calculator, I'm going to make sure I'm in radians because we're obviously doing calculus here. I'll do the cos of this, which is 4 pi over 3. So I will do the cos of 4 pi over 3, which is minus a half. So it's 8 pi multiplied by minus a half, which is minus 4 pi. So because they asked for the magnitude, we can just ignore the fact that it's a deceleration. So we can say it's a magnitude of 4 pi meters per second squared for part A of the question. Now for part B, it says the greatest distance. So we're interested in what x is going to be from O attained by the particle during this motion. So if I want to find out what x is equal to, we know that we're going from v to x. So we're wanting to go integrate. So we were going from v to a, so we differentiated. We are now going to integrate. So I'm going to integrate the v, which is 4 sine 2 pi t, with respect to t. So you think to yourself, what differentiates to sine? Well, it would be a minus cos. So there's going to be a minus cos of 2 pi t. The 4 is still there, but I'm going to have to counter that if I differentiated this, I would get that 2 pi. So I've got to divide by that 2 pi, and I've got to put plus c. Now I know something. I know that the particle is at O when t equals 0. In other words, when t is equal to 0, x is equal to 0. So I can find out what that constant of integration is. So I get 0 equals, when t is 0, I get the cos of 2 pi times 0, the cos of 0. The cos of 0 is 1. So it is just minus 4 over 2 pi plus c. In other words, this means that c is equal to 4 over 2 pi, or just 2 over pi. Hence, we now have what x is equal to. X is equal to, I'm also going to simplify that to just 2 over pi. It's the c part, which is 2 over pi, minus 2 over pi cos 2 pi t. Now, I want to find out what the greatest distance is. I want to think, when is this the biggest thing possible? Now, I'm just going to investigate what this part is. You might do differentiation if you wanted to. I don't think there's that much point in doing that. I think we can reason with ourselves of when does this reach a maximum. So this is going to be a maximum when this part that's being subtracted, I actually can make this become a minus 1. This smallest thing that this can be is minus 1, and it's being multiplied by negative 2 over pi. Negative and a negative will give us a positive. So I'm going to say it will be a maximum when cos of 2 pi t is equal to minus 1. So the maximum thing of x is going to be 2 over pi minus 2 over pi multiplied by minus 1. 2 over pi plus 2 over pi is just 4 over pi meters. So the maximum displacement is just going to be 4 over pi for that one that we've got there. Okay, so the next part that we're going to look at is this question. A particle P is moving along the x-axis. Initially, P is at the origin. So I always like to jot these things down. The displacement is 0 when t is 0. At time t seconds, where t is greater than or equal to 0, the velocity is equal to te to the minus t over 4. The first thing we're going to do, not the first thing, the only thing we're going to do is find the distance of P from O when the acceleration of P is 0. So we're going to have to do something to do with distance and something to do with acceleration. So I'm going to have to do some differentiation and I'm going to have to do some integration. I think what I'll do is I'm going to start off by finding out the acceleration. So to find the acceleration, I'm going to just differentiate, okay? I am going to differentiate this. Now, you guys are doing further maths. I hope you've probably already looked at the product rule to differentiate this. But I recognize this is an AS kind of part. So if you haven't learned the product rule for differentiation, you won't know how to do this part. But just bear with me, it's not too complicated. So what I'm going to do is I'm going to say here for the product rule, I'm going to say that U is equal to T. And I'm going to say that V is equal to E to the minus T over 4. So product rule, I'll differentiate both of these things. T differentiates to 1, and e to the minus t over 4 differentiates to minus 1 over 4, e to the minus t over 4. So product rule will have all those things being multiplied, the diagonals being multiplied and then added. So I'm going to do the t times this, so that's going to be minus a quarter t, e to the minus t over 4. Plus the other diagonal, which is just e to the minus t over 4. So I've found the acceleration, and I want to find out when the acceleration is 0. So when the acceleration is equal to 0, I get 0 equals minus a quarter t, e to the minus t over 4, plus e to the minus t over 4. I'm just going to factorize. I'll take out e to the minus t over 4 as a factor. That's minus a quarter t plus 1. This thing obviously can never be equal to 0, so I need that thing to be equal to 0. So I get minus a quarter t plus 1 equals 0, or 1 equals a quarter t, or t equals 4. So really what the question is now saying, it wants me to find the distance of P from O when the acceleration is 0. In other words, when t is equal to 4. So now what I'm going to do, and see if I can squeeze it all in on this same page, I'm going to find out what x is equal to. And I'm going to find out what x is equal to by integrating v, because I know I've shown you this before. To find out what x is, we integrate v, we go up that list. So I'm going to integrate t e to the minus t over 4 with respect to t. Now I'm going to just make it clear this thing was to do with our differentiation. I'll now do a different thing for our integration that we've got here. So for integration, to integrate this thing, we are going to have to use integration by parts. For integration by parts, my u is t, and my v dash is e to the minus t over 4. So I will differentiate u to get u dash, which is just 1, and they will integrate e to the minus t over 4, which is minus 4 e to the minus t over 4. Because you obviously have to counter the negative that's in here, and you have to counter the divide by 4 by multiplying by 4. Now, when we do integration by parts, we are going to do uv subtract. We've already used this pair that we've got here. We get this kind of shape here. If you've done my videos, you'll know what I'm talking about with this. If you haven't, just kind of watch what's happening. So it is going to be equal to uv, which is minus 4t e to the minus t over 4, subtract the integral of these two. Now, because you're subtracting a negative integral, it's the same thing as adding on the integral of 4e to the minus t over 4 dt. So that's minus 4t e to the minus t over 4. And when I integrate this, it's going to be minus 16 e to the minus t over 4. It gets 4 times bigger and it becomes a negative because of this negative a quarter. So we have the opposite of the quarter is multiplying it by 4. And obviously we're going to need a constant that we've got here, which is this. Now looking at the question, we know a few things. We know that when x is equal to 0, t is equal to 0. We used that earlier on. So when x equals 0, t equals 0, that will help us find out what c is. So that part's going to be a 0, and when t is 0, we just get minus 16. So we get minus 16 plus c. So c is equal to 16, which means that x is minus 4t e to the minus t over 4, minus 16 e to the minus t over 4, plus 16. Now we need to remember what the question actually said. We want to find the distance of p from O. We want to find out what x is when t is equal to 4. So when t is equal to 4, x is equal to minus 4 times 4, that's minus 16, e to the minus 4 over 4, which is minus 1, minus 16 e to the minus 1, plus 16, like we've got like this, okay? So all we need to do is do a little bit of factorizing. I'm going to take 16 out as the factor. So I have minus e to the minus 1, minus e to the minus 1, plus 1, which is just 16, 1 minus 2 e to the minus 1 meters that we've got for that part. So we've got the correct answer of 1 minus 2 e to the minus 1. Now, if they'd said for it to be as an exact value, we'd have to leave it like this. If they didn't, we could have literally just typed this into our calculator here and just rounded it to 2 or 3 significant figures. So I want you to have a go at this question that we've got here. It is a your turn question, and then you can have a go at doing some things from exercise 4A for this one. So a particle P is moving along the x-axis. Initially, P is at the origin. So I'm always going to write these things down. Initially, it is at the origin. And is moving with speed 2 meters per second in the direction of OX. So if we have the origin and we have x, the velocity is moving away from it. So it's a positive 2 rather than a negative 2. At time t seconds where t is greater than 0, the acceleration of p is 4e to the minus 0.5t directed away from O. So the acceleration is also going in this direction, which means the acceleration is positive. Away from O means that it is positive. We're going to find the velocity of p at time t seconds. Well, we know that the velocity is where you're going up that list, so we're going to integrate it. We're going to integrate 4e to the minus 0.5t with respect to t. So it's still going to be e to the minus 0.5t. I'm going to have to counter that negative, and I'm going to have to counter that 0.5, and I'm going to have to put on a plus c. Now, is there anything else that we know about this? We said initially, here we go, we know that initially these are the facts that we've got, so we can use that to find out what c is equal to. So 2 is equal to minus 8, because e to the 0 is 1, plus c, and so c is equal to 10, which means that our velocity is equal to 10 minus 8 e to the minus 0.5t. I've obviously just written the c part first, because I just prefer writing that with a positive thing to start off with. And obviously that's our in meters per second that we have for this. For part B, it says, show that the speed of p cannot exceed 10 meters per second. Well, this is all to do with your knowledge of functions and how well you know that these different parts of things are going to behave. So I'm just going to always start off. I'm going to start with this one and say that e to the minus 0.5t, if you think about that as a graph, it's a graph that looks like this. It is always bigger than 0, and that is for all values of t. Which means that minus 8, if you take that thing and you multiply it by minus 8, that thing is therefore always going to be negative. for all t. And then if I add 10 to it, hence 10 minus 8 e to the minus 0.5t is always going to be less than 10. So in other words, the velocity is always less than 10, meaning it cannot exceed 10 meters, meaning it cannot exceed 10 meters per second. Part C says to sketch a velocity time to illustrate the motion of P. If you've got a graphics calculator, this is incredibly easy, but if not, you can just reason through about your knowledge of how to sketch these kinds of graphs. So we said that this is the exponential of this part. If I multiply it by -8, it's then going to be flipped over so that it would be like that kind of shape, and then it's shifting 10 spaces up. So we know that there is going to be the asymptote like this, and it does say for just t being greater than 0, so it's going to be this kind of shape. The only thing we need to make sure that we're careful of is just saying what this line is. So this line is that v is equal to 10. And initially we can say what the velocity is going to be. So we know that the velocity initially is a 2 that we've got there. Not particularly drawn well to scale. Maybe it should have come down a bit lower, but this would still get all of the marks for this. So I'm hoping that this first part has just felt like nothing new, but you might do, if you're learning this in year 12 and you haven't learned all of integration yet, obviously you would have found this slide pretty difficult because of the product rule and integration by parts, and possibly some of the other bits of integration too. So do just make sure that you've done like a crash course and some of those bits with integration. Hopefully your teacher will have done that with you as well, so that you're able to access this part. So go and have a go at exercise 4A, and then the next one we're going to look at some A2 content, which is where the things are expressed as a function of displacement rather than a function of time.